Part 2 describes a generic process for solving engineering problems in terms of a set of intellectual tasks. Their sequential application directs the effort from problem definition to solution communication. The process is modeled as a flowchart consisting of 8 distinct intellectual activities. The purpose and function of each task is described with typical examples. Where the use of synthesis and analysis skills are important is identified. The process is initiated by some specified or recognized technological need. Otherwise, there's no problem to be solved. The need can arise from a variety of sources. Examples might include resolving an operational deficiency, introducing a new technology, satisfying an industry regulation, responding to a business opportunity, or meeting a safety requirement. The precise nature and scope of the problem dictates which steps will require greater attention. The first step in formulating a well-defined engineering problem is to thoroughly understand the operation and function of the system. This is critically important to establishing operationally defined solution goals that meet the initiating need. For example, it is not sufficient to ask if the output of a chemical process will be too hot if a heater is added to increase productivity. From an engineering perspective, an operationally solvable question would be what is the temperature of the process output if a 1,000-watt heater is added to the system and run at full capacity. Good problem definition is critical to the success of the solution process. It is a highly creative activity requiring the mental skill of synthesis. The next step is to conceptualize how a possible solution may be devised or consider what options are available to achieve the goals of the solution. In terms of the previous example, the heater to be added to the production system might be electrical or fed by process steam. The energy transfer mechanism might be conduction or radiation. The choice may be restricted by some physical or operational constraints of the system. Creativity and innovation are required to generate new ideas and different approaches. Formulating and dealing with all possibilities and deciding on a proposed solution concept involves the intellectual activities of synthesis and decision making. A mathematical model or physical prototype of the proposed solution concept that can be analyzed or tested is created in the third step. Only then can operational relationships among the physical variables involved be generated to produce quantifiable answers to the questions raised in the problem. Mathematical models or prototypes should be as simple as possible while still being relevant to the problem. Making appropriate simplifying assumptions is a skill that comes with experience. Put off second-order effects to subsequent investigations. The uniqueness of the model or prototype as an abstract representation of the system requires the intellectual activity of synthesis. The mathematical model or physical prototype must be provided with technical intelligence or operational capability. This permits its behavior and functionality to be analyzed and/or tested. In a mathematical model, this requires introducing symbolically the relevant principles of engineering and laws of nature that govern how the problem variables relate to one another. A problem involving a steel structure may require the application of the equations of static equilibrium. In a problem involving power utilization, the laws of thermodynamics would be more appropriate. In a similar fashion, a physical prototype must possess features of functionality that permit meaningful experimentation. This process step represents a transition to the intellectual activity of analysis, as the information being added is not being newly created. The model is now mathematically manipulated to extract the governing relationships between the important problem variables. This permits the system's performance to be understood quantitatively. At this point, relevant numerical values may be inserted to determine how the magnitude of the inputs and outputs behave relative to one another. Data taken from tests conducted on a prototype are analyzed to determine the relationship between input and output variables. These tasks are all deductive and analysis activities. Although the checking task is separated for emphasis, it is an activity that should be integrated into all aspects of the process. It should include items like ensuring unit consistency in equations, applying limiting case analysis to problem variables, checking algebraic manipulations, repeating numerical calculations to ensure correctness, determining if variables impact performance as anticipated, and reviewing the magnitude of calculated results as being physically reasonable. Checking should be included in all steps where the opportunity is available. These actions are all deductive and analysis activities. The evaluation and generalization step asks the following questions. Have the quantitative and operational questions originally posed in the problem been answered? Now that a relationship between problem variables has been developed, what does it mean in terms of general behavior of the system? Is there additional knowledge to be gained that may be of further or future use? Is it possible for generalizations to be made to give a better understanding of the behavior of the problem beyond that of the original answer sought? If the problem's solution is acceptable, the last step is to communicate these results and any other relevant information learned in generating the solution. This report should be succinct, meaningful, and understandable. It should not include the details of how the problem was solved unless requested. If appropriate, it might include suggestions on how to proceed in the implementation of changes or improvements to resolve the original need, or recommend additional investigations that might be helpful. If the answer to the original question is unacceptable or unreasonable, the problem has not been solved and the solution process must be repeated. This requires returning to some earlier task to correct a procedural error or generate a new solution approach. This can occur at any step in the process, making it highly iterative. An example would be recognizing there are insufficient equations in the computation step to obtain a relationship among the problem variables. This might require modifying the model or providing it with additional engineering intelligence. To rectify an error or inconsistency at any phase of the solution process dictates returning to an earlier phase to correct that difficulty before proceeding on. Some special concerns are worthy of mentioning before leaving Part 2. It is rare that the process will proceed smoothly from problem statement to solution without a number of iterations to earlier steps. This is to be expected. Getting stuck at some point can be very frustrating, but don't despair. Seek help from engineering references, colleagues, or even the internet to overcome blockage. Doing something different for a while can provide new insights. Using existing formulae that appear relevant is a temptation. It is better to begin with fundamental principles and allow meaningful relationships to generate themselves. Use potential solution software with caution. It may contain assumptions, approximations, or restrictions not applicable to the problem at hand. The 8 steps of the problem-solving process, summarized here for completeness, have been presented and discussed generically as to purpose and function. They clearly illustrate the logical progression of the solution process. The intellectual skills of synthesis and analysis are both necessary to the effective implementation of the process. Synthesis and creativity dominate the first 3 tasks, while the remaining steps primarily involve deductive and analysis activities. However, the need for both skills can also overlap in any phase of the solution. Part 3 demonstrates the application of this process to the solution of a real engineering problem.